Hi!
Hello!
Today we are going to dive into something super cool.
What is it?
Well, it's all about applying Pascal's principle in analyzing liquids in various systems. Sounds pretty cool, right?
Yes! Now, let the learning begin. Our objective is to analyze fluids in various systems using Pascal's principle.
It's trivia time! The first question is, can pressure be increased in a fluid by pushing directly in the fluid?
Yes, but it is much easier if the fluid is enclosed. The heart, for example, increases blood pressure by pushing directly on the blood in an enclosed system.
Wow! You are a great learner! Second question, what happens to a pressure in an enclosed fluid?
Since atoms in the fluid are free to move about, they transmit the pressure to all parts of the fluid and to the walls of the container. And the phenomenon is called what? Pascal's principle.
Wow! You are a great learner! Now, let's move on to the question. What is Pascal's principle? Pascal's principle, also known as Pascal's law, states that when a change in pressure is applied to an enclosed fluid, it is transmitted and diminished to all portions of the fluid and to the walls of its container.
Take time in reading this to understand the relationship between pressure, force, and area. Our formula is pressure equals force over area.
Now, let's move on to applications of Pascal's principle and hydraulic systems.
The first application is the hydraulic jack. Take time to read about hydraulic jack.
Another application is the hydraulic lift. A common application of Pascal's principle is a hydraulic lift used to raise a car off the ground so it can be repaired. A small force applied to a small area piston is transformed to a large force at a large area piston. If a car sits on top of the large piston, it can be lifted by applying a relatively small force to the smaller piston.
Now, you may question, what is a hydraulic system?
A hydraulic system is a drive technology where a fluid is used to move the energy from example given, an electric motor to an actuator, such as a hydraulic cylinder. The fluid is theoretically incompressible, and the fluid path can be flexible in the same way as an electric cable.
Take the time and read this to understand the relationship between pressure, force, area in a hydraulic system.
Now, according to Pascal's principle, this pressure is transmitted and diminished throughout the fluid and to all walls of the container. Thus, a pressure P2 is felt at the other piston that is equal to P1. That is, P1 equals P2. However, since P2 equals F2 over A2, we see that F1 over A1 is equal to F2 over A2.
It's pretty simple, right? Now let's move on to our example problems.
First example. A force of 100 N is applied to the brake pedal, which acts on the cylinder called the master through a lever. A force of 500 N is exerted in the master cylinder. Pressure created in the master cylinder is transmitted to four so-called slave cylinders. The master cylinder has a diameter of 0.500 cm, and each slave cylinder has a diameter of 2.50 cm. Calculate the force F2 created at each of the slave cylinders.
So, F1, which is applied to the master cylinder, is already given. The cross-sectional area A1 and A2 can be calculated from their given diameters, which means A1 and A2 will be divided by 2. Now note the formula given for the area of a circle. After substituting, A1 is equals 0.250 centimeters, and also A2 is equals 1.250 centimeters. Now after solving for the area of a circle, let's move on to the solution. So, Pascal's principle applied to hydraulic system is given by F1 over A1 equals F2 over A2. Now, to solve for the F of 2, the equation will be F of 2 equals A sub 2 times F sub 1 divided by A sub 1. Now, substitute the formula with the given numbers and solve. And then, cancel the cm squared. After solving, the final answer is 12,500 newtons. Now it's your turn to answer. Pause this video to read and solve the following problem. Ta-da! Here is the solution. If you answered correctly, leave a like.
That is all for today's video. Thank you for watching.
Okay, love you guys. Don't forget to smile.